The core challenge of machine learning is distillation. We're trying to extract predictable, understandable rules from the infinite complexity of the real world. In domains like image recognition or natural language, the data generating process involves so many latent variables that it effectively lies outside the mathematical boundaries of any model family we could ever construct. Use a simple linear equation and we underfit. Increase capacity, and a high-degree polynomial contorts to pass perfectly through every point, memorizing noise instead of the signal. There's an inherent mismatch between sprawling data and rigid model boundaries. The logical assumption is to carefully tune the number of parameters until the model is the exact right size to capture the trend without overfitting. But in modern deep learning, that is rarely the solution. Instead, we construct an enormous, deep model with a massive excess of parameters, and then we intentionally restrict its ability to use them. This deliberate crippling is called regularization. It is the mathematical mechanism we use to trade a slight increase in bias for a massive reduction in variance. It forces an overly complex neural network away from pure rote memorization, compelling the system to actually understand the underlying structure of the data. A standard training algorithm has a singular goal: navigate the objective function to find the exact weight configuration that produces the lowest possible training error. When we apply parameter norm penalties, like L1 or L2 regularization, we add an entirely separate mathematical term to that objective function. This creates a secondary force that actively pulls the weights away from that minimum error state. How the network responds to this pull depends entirely on the mathematical curvature of the cost function. The penalty interacts with this underlying geometry to selectively filter which information is kept and which is discarded. We represent this curvature using a matrix of second-order derivatives, known as the Hessian. The Hessian maps the exact multidimensional topography of our objective function. By examining the eigenvectors and eigenvalues of this Hessian matrix, we can see the precise mathematical mechanics a neural network uses to isolate a structural signal from random noise. To observe this filtering process, we can analyze a quadratic approximation of the objective function, looking specifically at the immediate neighborhood around the optimal unregularized weights. This diagram outlines that exact neighborhood. The solid ellipses represent the contours of the unregularized objective function. The center point, W star, is where the training error is perfectly minimized. Now we introduce L2 parameter regularization, commonly known as weight decay. This adds a penalty that drives the weights closer to the origin, represented here by the dotted concentric circles. Using Karush-Kuhn-Tucker multipliers, we can view this penalty as an explicit geometric constraint. The L2 term acts as a hard spherical boundary. The regularized solution, W tilde, is forced into an equilibrium where the objective contours strike this new boundary. If we solve for this equilibrium mathematically, we find that L2 regularization does not uniformly shrink the weights. It rescales the original weight vector strictly along the axes defined by the eigenvectors of the Hessian. Look at the vertical axis. Here, the objective function is highly sensitive to movement. The contour lines are tightly packed, meaning the Hessian has a large eigenvalue. The training data expresses a strong preference in this direction. Because this eigenvalue is significantly larger than our regularization penalty, the penalty has relatively little effect. The weight's magnitude along this specific axis is preserved almost intact. Now look at the horizontal axis. The objective function does not increase much when moving horizontally. The eigenvalue is small, indicating low curvature. Moving in this direction doesn't significantly impact the gradient. Because this eigenvalue is smaller than the penalty, the regularizer overwhelms the data's weak preference. The parameter along this specific flat axis is decayed almost entirely to zero. L2 weight decay is an eigenvalue scalar. It preserves parameters along axes that reduce the cost function and decays parameters mapping to uninformative noise. While L2 operates through continuous, proportional scaling, L1 regularization imposes a drastically different geometry on our parameters. Because L1 is defined by the sum of absolute values, its constraint region is not a sphere. It forms a sharp, multi-dimensional diamond. This physical shape alters the underlying calculus. The regularization contribution to the gradient no longer scales linearly with the size of the weight. It applies a constant factor,
pushing the optimization mathematically toward the diamond's corners, right onto the axes themselves. Assuming a diagonal Hessian where our input features are uncorrelated, the analytical solution reveals the difference. L1 does not multiply the optimal weight by a fraction, it subtracts a constant shift, determined by the penalty divided by the Hessian's diagonal. If the original unregularized weight happens to be smaller than this calculated shift, the penalty completely overpowers it. The value is forced exactly to 0. This exact 0 condition is called sparsity. L2 weight decay will shrink unimportant weights to microscopic fractions, but they remain active. L1 severs them entirely. Because its sharp geometric boundaries force parameters onto the 0 axes, L1 operates as an automated feature selection mechanism. It identifies unnecessary dimensions in the data and structurally deletes them from the model. We can step back from the abstract parameter space and look at the raw linear algebra of the training data to see these same forces at work. Consider an under-constrained machine learning problem. For example, a dataset where we have fewer training examples than input features. When we attempt to solve this system by multiplying the data matrix by its transpose, the resulting covariance matrix is singular. The data has true zero variance in certain directions, making the matrix mathematically impossible to invert. The algorithm hits a wall. But by applying an L2 penalty, we are directly adding our regularization coefficient to the diagonal of that exact matrix. This specific addition creates the Moore-Penrose pseudo-inverse. By injecting variance along the diagonal, we ensure that the previously unsolvable system is now mathematically invertible. Regularization acts as an algebraic stabilizer, allowing us to compute solutions for systems that would otherwise be numerically undefined. Norm penalties are just one execution of this concept. Regularization is any technique that trades bias for variance by encoding a prior belief about a simpler solution. If we inject random noise into the input data during training, we force the network to learn rules that are insensitive to small random variations. Mathematically, this is equivalent to placing a norm penalty directly on the weights. If we apply label smoothing, treating a strict classification of 1 as 0.9, we model noise directly onto the targets. This prevents the softmax function from aggressively chasing infinite weight magnitudes just to achieve absolute certainty. We can even regularize through the physical architecture of the network itself. By forcing different output variables to route through a single shared intermediate layer, the lower parameters are subjected to the pooled data of every task, structurally constraining them from memorizing domain-specific noise. In practice, engineers sometimes avoid continuous mathematical penalties entirely. They use explicit Karush-Kuhn-Tucker reprojections, simply clipping weights that exceed a threshold. This ensures the optimization procedure explores the space without driving units to 0 and killing them. Whether it's the geometric truncation of an L1 diamond, the stabilization of a singular matrix, or a shared node in a neural network, the underlying principle remains identical. We purposefully construct a system capable of immense, chaotic complexity, and then we introduce friction. We prune, penalize, and restrict. Regularization is the mathematical expression of our prior beliefs, the mechanism that constrains an algorithm toward generalizable patterns rather than historical noise.